things, both something that has to do with really the numerical method, which will be continuous time quantum Monte Carlo. It's something that I will mainly be talking about tomorrow. But today, to set the stage, I also want to introduce the theoretical framework for it, which is dynamical mean field theory. So my full title is a bit longer than this. Here's an important piece of information. I've put here this website here that you can go have a look at. I'll do it for you now just to show you. There are a couple of pieces of information that may be useful concerning the lecture itself. There will be lecture notes that I will post. They're not quite ready yet, but they will be later in the morning. So I'll put them online and you can get them through a link here. Also, a couple of times during the lecture, I may interact a bit with you through something which is called Book Lab, which is sort of a quiz that I can ask via your smartphones. You can access this via a QR code. I'll show you this in a second, but if you don't scan it and want to get there, you can also use the link that is here at the very beginning of this web page. Then concerning the tutorial, I'll talk more about this tomorrow, but if you want, you can already have a look at it today. We'll be using Jupyter notebooks, but I need a certain number of libraries to use that. So one way is to use something called the Binder project, which doesn't need any installation. But you may also want to try to install it on your computer. For that, there are installation instructions here, and you can try to follow them. I won't be really able to help you so much with the installation, but you can always ask something on the Slack, and I can try to help. And there's always the other option. Anyway, so that's that. Let me go back to my slides here. So let's indeed try to start and see if that works. You should be seeing a QR code on the screen, and if you take your smartphones, you can try to scan that thing, and it will bring you to a web page with the Book Lab quiz. So I'll let you give you a bit of time to try to do that and see if that works. I see some of you already managed. Otherwise, if the scanning of the QR code doesn't work, you can also just open a browser and connect to the website that is written there, booklab.com, with this identifier there. So I'll let you give it a try. I'll try it too, just to make sure it works. And so if this works well, it should bring you on your smartphone to something that looks like this. Yeah, so I see a number of you managed, like 66. That's almost everyone already. So that's not too bad. I'll give you a couple of seconds. Again, if at some point you lose this, you can always go to this webpage I was showing earlier and join the quiz from there. Okay, I think, wait one more second. Okay, that's already not a bad fraction. All right, so let's see if that works. So let's start with an easy one, just to see a bit how you're doing, and if you're ready for this lecture. Well, I see already at least someone is doing great. I see. Well, no one seems to be suffering too much from the altitude, which is a good thing. All right. Yeah, it's early in the morning, 9 o'clock. As you see, we're all equipped, so I also have the coffee. The good thing with this conference is that we are offering a free coffee. You just have to go to your kitchen and get some. Great. So I see most of you are doing pretty good. So let's go with another quiz. This time asking a bit about how familiar you are with a couple of subjects that I'll try to cover. I sort of want to have an overview what you already know, and where I should be maybe spending a bit more time. So there's different topics. One is strongly correlated systems in general at equilibrium, the many-body Matsubara formalism, DMFT, dynamic mean field theory, classical Monte Carlo, and quantum Monte Carlo, just to have a bit of an idea. Okay, good. Okay, that starts to look a bit like my expectations. So I see that at least not everybody already knows dynamic mean field theory. So that's certainly good. I'll spend quite a bit of time today to discuss this. I'll also spend, and actually Alberto told me to spend a bit of time sort of getting back to the, sort of give a bit of a refresher on many-body physics, or the many-body formalism. So this is also something I'll spend a bit of time doing today. I hope basically today to cover those first three topics. And indeed, tomorrow I'll mainly spend time talking about quantum Monte Carlo with a quick refresher about classical Monte Carlo, which you seem to be a bit more familiar with. Wonderful. Well, that gives me a good idea of where we stand. So I think we can start, and can give you a bit of an outline of what I want to cover. All in all, these two lectures will be about strongly correlated systems and how to treat them. One thing I have to say is a lot of the topics in the school will be about real-time evolution of quantum systems out of equilibrium physics. In this first lecture, I will really just focus on equilibrium properties. So there will be dynamics, quantum dynamics, but it's not out of equilibrium. There's no real-time evolution. So I'll discuss strongly correlated systems a bit in general in the beginning, give you a bit of a refresher in the many-body formalism that will be used both in the construction of the dynamical mean field theory, which will be what I hope to be covering today. And it will also be useful tomorrow when I talk about quantum Monte Carlo methods here. But I'll first do a quick refresher about Monte Carlo methods in general. And on Friday, we'll have the hands-on tutorial. But I'll tell you more about it tomorrow. Great, so let me start with strongly correlated systems, and here I'll just try to give you a bit of the motivation for all of this. So I'll be scribbling notes. Again, there will be lecture notes, so don't worry, I won't be writing too much here, mainly equations. But you'll have more information in the lecture notes that are going to be ready later today. So one of the challenges of modern quantum mechanics is to describe the behavior of materials, of the way electrons behave in materials. And so that's, I would say, the motivation. And for that, you, in principle, need to solve something like a Hamiltonian, which would be, and now forget about here the ions, as I'm already using what's called the Born-Oppenheimer approximation, where the crystal is sort of fixed, and I'm only interested in the electronic degrees of freedom. I would still have to solve a Hamiltonian, which is something like a sum over the kinetic energy for all the electrons. That's this first term. A term which describes the interaction, the electronic repulsion between those electrons, which goes like E squared divided by the distance between two electrons, and a term which is connecting the electrons and the ions, which involves the number of positive charges in the atom, in the nucleus, and the electronic charge, which again is divided by the distance between the electron and the ions, the nuclei. So in principle, I'd have to solve this, but this is a very difficult problem. We'll come back to that. This is not a Hamiltonian. While it's easy to write, it's something that I cannot solve exactly. But one of the great successes of the description of solids is something which is called band theory, or electronic structure theory. So band theory is something which simplifies this Hamiltonian here and describes electrons as if they were evolving alone, but in an effective environment, which is sort of mimicking the effect of all other electrons. So it turns this Hamiltonian age, like this is age full. It's approximating this to a single particle Hamiltonian, just one electron evolving in an effective electronic field, if you want, electronic bath. So that's an approximation, but it's surprisingly efficient. So even though we really remove explicitly the interaction between the electrons, if we're clever enough about the way we define the effective field in which those electrons are moving, that single particle Hamiltonian is, for a very broad class of materials, actually a very efficient way to describe their electronic properties. So that's probably one of the really great successes of condensed matter theory. But there's always a limit to this kind of approaches. And in materials for which this interaction term, the correlation, if you want, between electrons, the Coulomb repulsion between them becomes too strong, well, this band theory approach breaks down. And for those materials, we call them strongly correlated materials. So that's what I mean when I say strongly correlated material. What I mean is that basically band theory fails. So for some theorists like me, this is basically where things get interesting. So I'm basically interested in those materials or in those electronic systems where a single particle picture or band theory per se fails. So those systems generally have, so strongly correlated systems have fairly sophisticated phase diagrams. So one example, here are just two. I mean, I could spend a lot of time showing all sorts of examples of sophisticated phase diagrams. I picked one that I sort of like, which has to do with materials that are called cuprate superconductors. So they belong to a family of materials which are transition metal oxides, which are materials for which there's often quite strong correlations, because in transition metal oxides, the D shell is the relevant one, and the D shell is sort of fairly localized. So electrons are not as delocalized in other materials. And this sort of strengthened the effect of electronic correlation. So cuprate superconductor, which are basically planes of oxygen and copper atoms, belong to that family. And this is a typical phase diagram you'll see for those materials. You see many different phases. So that's temperature. And that's what that P here is changing. If you want the whole concentration, it's changing the effective number of electrons in the system. And you see many different phases, antiferromagnetism. Of course, this dotted line here is superconductivity. So that's why these materials are quite exciting. They have very high temperature transition here. But then there's lots of other regions, the pseudo-gap region, semi-metal, bad metal regions. They're quite sophisticated. So that's typically the sort of phase diagram you'll meet for a strongly correlated system. Let me introduce that in the notes that we had previously. So I'll just copy that here. Try to insert that somewhere. So that's one example. Another example of a phenomenon which is quite striking in strongly correlated metals is what's called the Mott metal insulator transition. So in band theory, what basically predicts whether a material is insulating or metallic is basically only related to how many electrons you have. You have a certain number of bands in your system. There's band gaps between those bands. And as you reach some fillings, the system has a gap and is insulating. But for a system that has a filling which is not exactly filling a band, your system will always be metallic. So in principle, changing the interaction in those systems should never turn a metal into an insulator, but there are systems, strongly correlated systems, for which this is happening. So by changing some external parameters, so here, this is an example for V2O3, again, a phase diagram as a function of temperature and doping concentration. This is really applying pressure on the system. It's not really for all of these concentrations. You can think of this as just applying sort of a pressure on the system. We're not really changing the number of electrons. But we can lead the system from something which is a metal in some regions and have a transition to an insulator, which is really driven by correlations and not by the change of the number of electrons. You also have transition then at lower temperature to an antiferromagnetic state. So that again is the sort of phase diagram that you can find for a strongly correlated system. And that's what we have in mind, or I have in mind, when I want to construct a theory to describe these guys. Let me just put that other example here as well. Just as an illustration of what those systems can be. So in order to make progress, we could start from this complex Hamiltonian that I wrote here, but strongly correlated systems are really quite challenging. So it is a good idea to start from a simplified model and try to already understand the properties of simplified models and see what we learn from them, even if they're not a very faithful description of a material. And the main model that I will be discussing all over these lectures is the Hubbard model. So I suppose you've probably heard about that model before. It's, I would say, in quantum mechanics, it's a bit like the Ising model of classical statistical physics. It's sort of the simplest quantum correlated model that you can think of. And so let me try to describe it for you. And that will really be the sort of guinea pig of strong correlations that we'll be interested in. So the Hamiltonian for the Hubbard model is something that looks like this. It's written as a sum over indices I, J, sigma. I'll tell you in a second what all of these guys are. And it has two terms. The first term is a kinetic term. So typically the Hubbard model is defined on some lattice. So we can think of it as being, say, defined on a square lattice. And every site on the lattice has some label I or some label J. So those are the labels that you see in this sum. It's a sum over all the sites of a lattice. Sigma is the spin. And this is a hopping term. So this is destroying an electron on site J that has a spin sigma, and it's recreating another one on a site I with spin sigma. So that's defining a process where an electron hops from site J and jumps on site I with a hopping amplitude, which would be the modulus of that prefactor here. So that's the kinetic term of the Hamiltonian. But that, of course, per se is something that is easy to solve. So it becomes more interesting when we have an explicit interaction term. And the simplest one we could think of is a term like this, which basically gives you a penalty U. So U will be the Coulomb repulsion, or the energy you pay when two electrons are sitting on the same site. You see that term is zero, except when both Ni up and Ni down are the same, which means that we have two electrons on a site. So there are basically four options. I mean, this is a single band model. Now there's a single orbital. And so basically there's only four states on every site. So on a given site I, you'll have four possible states. Either the site is empty, or it has a spin up, just a single spin down, or two spins. If you want, it's doubly occupied. And so you'll pay the Coulomb interaction when you have two spins sitting on the same site. Otherwise, you don't pay that extra term here. So that may sound like a very crude approximation of a real material, especially if you look at this Hamiltonian that I was writing here. You see that the Coulomb repulsion is really something that decreases as 1 over the distance. So it's not something that is very local. This is not a decay that is extremely quick. So it may sound like a really quite dramatic approximation to make it entirely local. But actually, there's a bit of a rationale behind this. Is in a real material, there's screening from the other electrons. So if I just take a pair of electrons and think about their Coulomb repulsion, they will be surrounded by a cloud of other electrons that have a tendency to actually screen the interaction or the Coulomb repulsion between these two. And so effectively speaking, from the point of view of a single electron, the Coulomb repulsion is actually something that decays because of screening quite a bit quicker than 1/r. And so having an approximation that this is quite local is maybe not that bad. And actually, in a number of cases, the Hubbard model, at least at the qualitative level, sort of gives a reasonable description to some classes of materials that are strongly correlated. So, how hard is it to solve that thing? It looks like it's extremely simple to write. So can we actually solve that? Can we solve that guy? So there are some limits where we can actually solve this model. One limit, which is quite clear, is the U equals 0 limit. This is what we call the non-interacting limit, right? I turned off the interaction or the Coulomb repulsion between the guys. So whenever I'll say non-interacting later, that's basically what I mean. I mean systems for which I've turned off the U. Well, in that case, the Hamiltonian only has this kinetic term right here. This is a quadratic Hamiltonian, and it's something that I can diagonalize by just going to Fourier space. So in that case, I can just write H. It will become some sum over K and spin of epsilon K, C dagger K, sigma, CK sigma went to Fourier space. And basically that epsilon K is nothing but the dispersion of your lattice. So it depends on the details of the hopping amplitudes here and the structure of the lattice, but it's something that is in general easy to compute. And that's nothing but, if you want, band theory in its simplest version. So that guy here, if you want, is the dispersion of the lattice. Okay, so that's one limit which is quite easy. There's another one which is also easy. It's the one, of course, when everything, all the hoppings are equal to 0. This is still something I can solve because in this case, okay, this is vanishing. I just have that second term, but all the different sides are no longer talking to each other. So it's like a bunch of disconnected sides. So to solve the model, it's enough to solve just one of those isolated sides. We often call this the atomic limit. And
excuse me, Michel, can I ask you a question? Sorry for not raising a hand because for some reason I just can't do that.
No worries.
I don't know why. Sorry, but I would like about the non-interacting limit. My question is whether we are at this point talking about purely translationally invariant problem or
yes. Like, sorry, I should have probably mentioned this. So in all of that I'm going to say, I'm actually going to treat translationally invariant systems, of course. So I suppose that my lattice is translation invariance. So I will not be interested in disorder or things like this, which of course change the picture. If you introduce disorder in this system, it can become a little more tricky to solve. Yes, good point, thanks.
Yeah, because like your Tij amplitudes have indices which are position dependent, and this probably implies that they might be non-translational invariant.
Yeah, so I could have written this as Ti minus J if you want to.
Yeah, okay,
make
thanks.
it clear that I have translation invariance. Thanks, good point.
Michel, there is a second question in the chat. I can read it for you if you want. Sure. So it's a question by Sani Ghosh asking, the original Hamiltonian does not have any external potential. However, U seems to be arbitrary. Is there a way U is related to the Coulomb potential?
Yes, so there's, so U definitely has here in this simplified form is something that quantifies the strength of the Coulomb interaction. Now there's a full, of course, business, which I'm not describing, of deciding how do I start from such a Hamiltonian and make and construct the effective Hamiltonian here. This procedure, it's quite a complex one because we start from something that has many orbitals. Some of them are correlated, some of them are not very correlated. And so there's a lot of activity in trying to do something which is called the downfolding. So one starts from the set of, say, not too correlated or weakly correlated orbitals, tries to integrate that problem if like almost exactly, and sort of project this into an effective low energy interacting Hamiltonian. But that's a fairly complex. It goes through projections which depend on the actual structure of the orbitals and so on and so forth. And after you do this, you get this U, or you can get an estimate of this U, which is some sophisticated linear combination, of course, of all the structure of the lattice, the orbitals, the position of the ions, and so on. So it's a tricky thing to do, but it can be done. Yes. So DMFT has been used a lot, or the Hubbard model has been used a lot to try to describe strongly correlated materials, but also in a realistic context for which you actually try to put numbers, realistic numbers on those parameters. Even though here I'm describing the single band, single orbital, of course, for realistic materials in general, you want to go to something which will be the multi-orbital Hubbard model generalization of this. Great, so if there's no other question, I'll just move with the atomic limit. So again, here I have a bunch of isolated sites. So they're isolated sites, and those are easy to solve because the associated Hilbert space is only of dimension 4. There's just 4 states, so I basically have to diagonalize a 4x4 matrix, right? So that's something I can still do, and I can solve this exactly. But other than those 2 limits, well, unfortunately, this is a really tough problem. To give you an idea of why it's difficult, one can say, okay, let me try to solve this exactly using, say, exact diagonalization. How far can I go? Well, as you see, a single site has already 4 states, and the Hilbert space for the full system will grow as 4 to the power n. So why is it hard? Why is it difficult to solve? Well, the Hilbert space grows like 4 to the power the number of sites in your lattice. This very quickly, this exponential number grows huge extremely quickly. In practice, doing more than 10 to 20 sites is really impossible, and even there I'm just talking about getting the ground state. Getting the full spectrum would be really difficult. So like direct approaches like ED, exact diagonalization, will really suffer from this exponential explosion of the size of the Hilbert space. So that is why it's difficult from a numerical point of view. From an analytical point of view, there are not so many solutions either. There are some special cases, like in 1 dimension, where there's an analytical solution in some cases from something called the Bethe ansatz. And there's another limit, which is basically dynamical mean field theory, which is the infinite dimension limit, where this can also be numerically solved, or exactly solved, but numerically. So in 1D, we sometimes have Bethe ansatz. In infinite, so you will understand later what I mean by infinite D. This is basically dynamical mean field theory. And anything between those 2 limits has no exact solution, neither analytical nor numerical. So you can say, of course, ED is sort of the brute force approach, but there are more sophisticated algorithms like quantum Monte Carlo and things like this. Do these guys work well? Well, they certainly allow to make progress, but they all eventually suffer, especially in the limit where the system size becomes large. So the different algorithms suffer from different problems, but oftentimes we call this common problem for all these algorithms something that is called the fermionic sign problem. I'll come back to that. So most of the Monte Carlo approaches, numerical approaches, suffer from something which is called the fermion sign problem. And I'll talk about this more tomorrow when we talk about algorithms, but that's definitely an important limitation in numerical approaches. Okay. So I would say that a direct approach to the Hubbard model is something quite challenging. And this is the reason why there's been a lot of effort in trying to find clever approximations to nevertheless make progress and get some insight about the Hubbard model. Okay, I would say that closes the motivation part. Maybe I can take some questions if you have.
Michel, just before, there is a question by Anton.
Yes.
About the beta lattice. He's asking, is the beta lattice or something similar implied infinite dimension?
Not necessarily. So I'll discuss this when I talk about dynamical mean field theory. No, actually, the infinite dimensional limit doesn't really is not specific to a given lattice. It's what it really means is that it becomes valid for lattices in which the coordination number, which means the number of neighbors of a given site in the lattice, goes to infinity. That's so whether this lattice is a hypercubic lattice, whether it's the beta lattice or another one, doesn't really matter. What matters is that the number of neighbors has to go to infinity. But I'll actually discuss this when I talk about DMFT. Are there any other questions? Okay, well, if you don't have questions, then I will.
There is a question.
Oh, there is a question, yeah. Okay, Andrei Klibicki asking, how about the perturbation theory in U? How bad is it and why?
Well, that's an excellent question. Actually, it will be very much what we'll be discussing tomorrow. So I'm not going to give a full answer. Of course, we can start with the perturbation theory, which will work for small values of U. So we can do second order perturbation theory, and there's a regime where this will work. As U increases quite quickly, this will no longer be a good approximation, and you want to go to higher perturbation orders. And this is exactly what I'll discuss tomorrow. All right. Well, if there are no other questions, let me ask you a couple here about what we just discussed. I hope you still have the link on your smartphone. Wow, great! Well, you guys are doing fantastic here. You're definitely going to the right answers. So indeed, strongly correlated systems, almost by definitions, are those that cannot be described by some effective single particle Hamiltonian. The second one is a tricky one. I'm happy to see that you got this one right. I mean, the Hubbard model is not directly realized in a material, because in any material there's more orbitals and there's nothing like really a single orbital model. But actually in cold atomic experiments, one can create an artificial lattice, an optical lattice in which ultra cold atoms are trapped. And in those systems, one can actually effectively realize directly the Hubbard model and sort of have a quantum simulator of the Hubbard model directly. Yes, the Hilbert space does not grow like 2 to the power n, but 4 to the power n. And as we discussed, there are exact solutions in 1 and infinite dimensions. Great. Well, you guys are doing fantastic here. Okay, that's for later. So let me move on. Sorry, I have to get back to my slides. So I'll try to do a quick refresher in equilibrium many-body formalism, introducing the objects that we'll be talking or using a lot in the construction of DMFT and the continuous time Monte Carlo. This is in no way going to be a consistent and full, introduction. I'm just trying to introduce those objects that are going to be the most useful ones for the rest of the lecture. In the notes, I'll put some references about a good book where one can start and have more information. So let me call this is sort of a many-body refresher. And there, the challenge, one of the main things that changes when you start from, say, single particle Hamiltonian, like in band structure theory, there, describing the system and its excitations, it's quite easy because the eigenstates of the Hamiltonian are Slater determinants, and you know what you're doing, you know how to describe the state. At zero temperature, you would basically feel the energy levels gradually up to the Fermi energy. You can describe the excitations around the Fermi energy, define the Fermi surface, and so on. But as you go to an interacting system, things get a lot harder because there's no such thing as a Slater determinant being an eigenstate of the Hamiltonian. Any eigenstate is going to be a linear combination of basically all or a good part of the Slater determinants. So how do I, translate all the things that I knew, like Fermi surfaces and excitations, in the language of many-body? It's actually, even if I could solve the problem and I had those eigenstates, they would still be very difficult to manipulate their vectors in a huge Hilbert space. How do I, work in this formalism efficiently? So one way to do that is to sort of think a bit like an experimentalist and say, I will not try to actually manipulate directly the full wave function of the system, which is too heavy, but instead I'll try to work with objects that sort of probe my system. It's not going to give me the full information of the system, but it's going to give me some useful information about it. And before anything else, let me again emphasize that I will be talking only about equilibrium, right? And only about fermions. So a lot of what I write has generalizations for out of equilibrium and also can be treated for bosons, but I will just really focus on this here. So one of the main objects that actually does that, which is sort of a probe of single particle properties, is something called the green function. And it's going to be one of the main building blocks of a lot of what I will discuss later today. So there's actually a full zoo of green functions. They come in many different kinds. I will not introduce all of them. I'll just introduce the ones that are relevant for me. And one of them, I'll just give its definition and then discuss a bit what it is the retarded green function. So it's defined as GR, like R for retarded. It's a function of the position and the time twice. So let me just write what it is, and then we can discuss how to interpret it. So it's an average value of an anti-commutator between creation operator at R at time t. I mean the destruction operator, sorry, and a creation operator at R prime at time t prime. So that's the definition of that object. So just to make the different pieces clear, so this here is an anti-commutator. This guy here is an average, which is defined as average of A is one over the partition function trace of e to the minus beta h A. So here I'm using the fact that I'm at the equilibrium. So I'm using the Boltzmann factor to do my average. And my operators C and C dagger, they're expressed in the Heisenberg picture. So if you want C R of T is the Heisenberg evolution of the destruction operator CR. So it's something like this that involves the full Hamiltonian. So it looks like a fairly complex object. It's called a single particle object because basically what it tries to describe is the evolution or the amplitude for an evolution of a particle being created at position R prime at time t prime and evolving to the time t at position R. So it's giving me information about how single particle, if you want, excitations evolve in time in the system. Okay, so it's not giving me the full information about the system, only something about single particle excitation, but that is something that is actually relevant to experiments, which one can measure, and I'll come back to that. Okay, so that is a very important building block. And to connect with experiments, I want to introduce something which is very important, which is called the spectral function. Oops, sorry, wrong. Do that again. So the spectral function is something that is directly related to this retarded grid function that I introduced. In particular, I can Fourier transform my G and get that retarded grid function in reciprocal space in K and omega by doing a Fourier transform. So it's the usual Fourier transform. I do a Fourier transform in space, and at the same time a Fourier transform in time of my Green function that I introduced earlier. Okay, the reason I can do this Fourier transform is that you can show that this object has time translational invariance and space invariational it's invariant under translation in space at equilibrium. Okay, so I can take that Fourier transform and get that same object in K and omega. And something that you can show, and this is where the spectral function comes in, and this is an important result, is that you can always write this G of R K omega as a funny integral like this. So let me write it and then we can discuss it. So here I introduced an eta, by the way, sorry. Eta is a small positive number. It has to be introduced so that those integrals converge. Don't mind too much about it, but it's basically something that regularizes the integrals, and it's needed, and it's also appearing here. It's giving a bit of complex I here in this fraction to avoid some divergences that would come from this guy being equal to 0. So this is a spectral representation of the Green function. It basically says that you can obtain G equivalently from an object A, which is a real function called the spectral function. So this is the spectral function. It's a real function. And if you do this construction here, which is called the Hilbert transform, you can obtain the Green's function. So it may be strange to introduce it this way, but it turns out that this object is actually the one that is maybe most directly measured in experiments. So this is why this object is useful. But knowing G of R or A is really the same thing. And for example, you can immediately see by working a bit with this formula that A of K and omega is really nothing but -1 over pi of the imaginary part of G of R of K and omega. So knowing the spectral function or knowing G is really the same thing. They carry the same information. So why is this object useful? Because it's basically something you can get in some experiments that probe materials. One of them is the angle resolved photoemission spectroscopy. It's something where you take your material, shine some photons on it to extract an electron whose energy and momentum you can measure. And from that, you can get some information about the material, and you can show that what you actually measure is almost the spectral function. It's well, of course, there's matrix elements and so on, but it's basically the spectral function multiplied by the Fermi function. So you actually don't get the full spectral function. It's more like you get the negative energy part of it. And this is basically because you're probing only occupied states. Another experiment is scanning tunneling microscopy, where you use an STM tip to probe the material. And from that, you can extract the local spectral function. So you lose the information about the momentum, but you get something, the full frequency dependence, but of the local object, so the sum over K of AK omega. So when you want to relate to those experiments, this spectral function is really the key object. Okay, so oftentimes we'll try to interpret a bit the physics by looking at this spectral function. So let me discuss. Those are formal objects, but it's useful to know what they look like in some simple examples. So let me just take the case of free electrons, which is quite important to remember. So let me just give you that example. And you can work out what the green function in that case looks like, and same thing for the spectral function. So I'll take a Hamiltonian, which is just sum over k of epsilon k, c dag k, ck. You may notice many times I forget about the spin index because I either digest it into k or just simplify things a bit. In that case, you can show that the retarded Green's function of k and omega has a very simple form. It actually looks like 1 over omega minus epsilon k.
Michel?
That's I eta, yes?
Yeah, there is a question by Mark Villa.
Yes.
He said, I thought that RPS gave the bands of material. Then what is the relation between E of k and A of k omega?
Well, I'll come to that in 1 second. Okay. Yeah, give me 1 second and you'll see the connection between the two. But it's a very good question, and indeed there's a relationship between the two.
There is a question before, sorry, another one. Okay, if A of omega prime is purely imaginary, won't this transformation, which looks like Kramer's conic transformation, just give the imaginary part of the complex function?
Yeah, actually, this is, this in a sense is the Kramers-Koenig relation is a bit more general than this in principle, because it can be used for other objects, but that's exactly what it is. This is basically saying that this object is sort of the Kramers-Koenig of the imaginary part here, but that object here is real, right? This is a real object, while G of R here has both real and imaginary parts. But this is very close to a Kramers-Koenig transformation, indeed. That's a good point. Okay, so let me try to connect to the other question then. For free electrons, if I compute G of R and I compute the spectral function that goes with it, well, you can immediately see, this looks very much like what we had downstairs here, but I basically need to take A as being a delta function to eliminate the integral. So in the case of free electrons, A is a very trivial function. It's a delta function of omega minus epsilon k. So that's exactly the answer to the question here. The relation between A of k and omega and epsilon k is what you're looking at here. For free electrons, if I fix k and look as a function of omega, A of k basically has a very sharp peak at epsilon k. And so if you were to map A of k and omega at omega is equal to 0 over the Brillouin zone, you would basically see the Fermi surface, or if you trace it for a given epsilon k, you would see basically the band dispersion of your system. So for free electrons, the spectral function is very much carrying the same information as epsilon k. Right? But we're looking at interacting systems. So for interacting systems, this A of k will be something slightly different. And what you see is that interactions will broaden. So we'll have to understand what this means, but they will broaden A. So with interactions, instead of having this delta peak, you will start seeing something which starts to have some width here if interacting. So that's what's going to happen as I go away from free electrons. My spectral function is going to have some width, and this is related to the fact that now electronic excitation don't have infinite lifetime anymore. They decay in time. And the decay, the fact that they relax because they interact with their environment, this relaxation time is actually related to the width of this spectral function. So when it's very narrow, you have a long relaxation time. The broader it is, the quicker the system sort of relaxes. Okay. So in the general case, the Green's function will not just be that simple expression here, but it's something that will have interaction effects, and those can be encoded in yet another important object. So the GR in general will then look like something like 1 over, very much like a free electron, so what I had written before, minus epsilon k, but with some corrections that I can entirely describe in an object here, sigma, which is called the self-energy. So the self-energy is sort of the many-body object that encapsulates, that contains all the effects of correlation. So if you want, it contains or describes effects of correlations. So very often that's what we're trying to compute. We're trying to equivalently compute either the Green function or compute the self-energy that has the information about, if you want, the effects of correlation. And the larger, in a certain sense, the larger the self-energy, the larger the interaction effects, and the broader this kind of features. So if I go back to sort of a realistic system, I mean, this is not an experiment here, but it sort of shows how the spectral function would be for almost free electrons, which is that picture of that delta peak we were looking at with a tiny bit of broadening. And as I increase k, this moves just like the band. So this has a dispersion which looks like very much like epsilon k. In a correlated metal, you would see something quite different. You'll start to have a redistribution of the spectral weight, and those peaks will now have more structure. Something still remains at, say, the energy, the original dispersion, if you want. But then because of correlations, the spectral function acquires a more sophisticated structure here, and there's a redistribution of the spectral weight. So that is a realistic spectral function for a correlated metal. And this is an information which is described in the spectral function and in the self-energy. Okay, great. One more object before I switch to DMFT. I see that I'm a bit slow here, but I'll nevertheless take time to introduce this one, which is yet another Green's function, which is actually the one that we obtain when we do those quantum Monte Carlo simulations. So the retarded Green's function, which is expressed here in real time, would be the best one if I directly wanted to connect to experiments, but it's not the one that is easiest to obtain from an algorithm. There's one which is a bit easier, which is called the Matsubara
Michel,
function. Yeah,
there is a question. Is the spectral function somehow related to the lifetime of the quasi-particles?
It is. So it's the width of that. If you look at your spectral function and you look at the width here, so if that width is a gamma here, the lifetime, if you want, goes like 1 over gamma. So if you can identify in your spectral function something which is your electronic excitation as a peak, looking at the width of that peak gives you a bit of information about the lifetime of the excitation. So for a non-interacting system, the width goes to 0 and the lifetime goes to infinity. The broader the peak, the shorter the lifetime. Okay. So let me introduce yet another Green function, which is called the Matsubara Green function, and is defined as so. So I'm changing my notation, and you'll see that I'm introducing a couple of new objects here. CR of tau, C dagger prime of tau prime. So there's a couple of new things here. Okay, the average is the same, but the first thing that has changed is that I'm using now a variable tau instead of t. And this tau is, yes?
There are other two questions. So
yes.
Mark Villa, in this general case, you don't have the integral over W prime. Is the integration already been done?
In what general case? Sorry, I have to understand.
I think is a.
Oh, you're talking about here.
Yes.
I mean, there's two equivalent ways to write GR. So I can definitely rewrite this GR as an integral like I have here. And I would find the spectral function. But I can also write it like this. So I can, instead of having the integral, I can encapsulate the omega dependence in the self-energy. So there's those are two different ways to write, but they're equivalent. So I can also write this as an integral of the spectral function, but there's no spectral function in this formula. Instead, the information is coded in the self-energy.
And always on the self-energy, there is another question. This expression reminds me of the mass renormalization in QFT due to the self-interaction.
Yes, there's definitely a link between the self-energy and the renormalization of the effective mass, if you want, of the quasi-particles. So if the self-energy here, it will have a linear term in omega. This basically gives a different effective weight, if you want, mass to the electrons. And this is, again, somehow related to the width. This time, not the width, but rather the integral of the spectral function. So in cases, as I was showing here, you see that if I integrate the spectral weight here, it's a smaller number than if I were integrating what I had originally on the other side. And this is a translation of the fact that the effective mass of my particle has increased. So yes, this is indeed, there's a relationship between this. And if I look at this at low energy and cook up an effective theory, I'll see that my effective mass has increased because of interactions. That's correct. Very good point. Sweet. So the Matsubara-Green function are defined in a time tau. We call this an imaginary time. It's a real variable, so it's not an imaginary time really, but you'll see why it's called like this in a second. This time its time evolution of those operators is given by this. So it looks very much like the Heisenberg picture, which we have on the other side, but it's as if I had taken the real-time t and I had made it imaginary and transformed t into minus I tau. So it's almost as if I had done t goes to. So it's sort of a transformation of the formalism in which it's as if I was working originally with imaginary times, even though here tau is really a real variable, okay? So that's a first change. And then there's this funny operator t, which is a time ordering operator. This is called a time ordering. And what it does, it brings the operators that have largest time to the left. So basically, if I take t, I will have to switch pages. Unfortunately, I hope you had time to write it. But if I take t tau of, say, a tau b tau prime for fermions, this will be a tau b tau prime if tau is larger than tau prime, and it will be minus b. It brings the largest time to the left if tau prime is larger than t. But because we're dealing with fermions, we also get an extra minus sign here. Sorry, that should be an a. I erased everything like this. All right. Now, this object may sound a bit funny. We're working in imaginary time. Does it make any physical sense? Well, this tau doesn't make really physical sense, but we can nevertheless connect this Green's function to the retarded one I introduced before. But it takes a couple of observations. The first one is that this g, seen as a function of 2 times, is also at equilibrium invariant. So it's a function of tau minus tau prime only in all cases. And it has another funny properties. If I take g at tau plus beta, where beta is 1 over the temperature, this is nothing but minus g of tau. So if you want, the function is antiperiodic in beta if you want. So you'd say it's quite different from the real time. In real time, of course, the time takes any value all the way to infinity. Here, tau is sort of it's closer to an inverse temperature. It takes values everywhere, but the function has some anti-periodicity. So in practice, it's enough to have all the information if I only consider the function in the interval between 0 and the inverse temperature beta. So if you're not used to that formalism, that is quite strange, but you know, it's like quantum mechanics. You never understand it really, but you get used to it at some point. And so in the tutorials, you'll play a bit with those functions to, you know, to get a bit of a feeling of what it is. Now, because there's this because the function is antiperiodic, you can actually Fourier transform it and get a g of k and I omega n. But because the function has a finite interval over which is antiperiodic, now the frequencies are not, they're discrete, right? So the Fourier transform is an integral from 0 to beta only of e to the I omega n tau, my original g of k tau. And those frequencies, they're not any frequencies, they're discrete. So I omega n, they're called Matsubara frequencies, and they're given by this with n belonging to z. So those guys are called Matsubara frequencies. Okay. So you can take that function in Fourier space, and then again, it would be a function of k. There's no difference here, but now I look at the function over those imaginary discrete frequencies, which are the Matsubara frequencies. So how the hell is this function in any way connected to the other one? Well, I did this strange transformation of time becoming imaginary, but how do I relate those things now that I've done all these manipulations? Well, what's quite amazing and what it can show is that there's also a spectral representation for this Matsubara Green's function. It also has a spectral representation which reads actually exactly like the other one. And that's how they connect. There's also an expression like this, but this time I put I omega n here instead of omega. And I write it like this. It's exactly the same formula as before, except that I've put I omega n here instead of omega. And that spectral function is the same as for the retarded. So that spectral function here is identical to the one for GR. So you see those two functions, G, the Matsubara in imaginary time and imaginary Matsubara frequencies, and the retarded one, they come from the same spectral function. And actually, if you want, the spectral function defines through that transformation a function G all over the complex plane. I mean, I can actually do that by saying, let me take a completely general G of Z, where this is any complex number, and write it like completely generally like this. Oh, sorry, that should now be Z here. Z minus
Michel, there is a question by Thomas Michel asking,
yes.
why does G before the Fourier transform depends on K inside the integral?
Oh, it probably should. You mean why did I forget to put the K dependence here, for example? I mean, yeah, here I forgot clearly the K dependence. So this is definitely K dependent. All the Green's function objects are K dependent. So I probably forgot it here. So of course this is still a function. These guys are still a function of K. I just made the notation a bit.
And Edith Jukuo asking, okay, the Matsubara Green's function A of tau and B of tau prime, are they operators?
Yes, these guys are indeed. This is a very general definition of what this time ordering operator does, and it's indeed acting on operators that are expressed in the picture, in the imaginary time picture. So A of tau, what this really is is, if you want an operator, well, then I can actually write it here. An A of tau is, if you want, the time evolution of an operator. And this is indeed an operator.
Okay. And yeah, and there's another question. Either I'm eta missing in the denominator for the Matsubara-Green function.
No, actually, and so in this case we get lucky, because the reason why we've put the I eta here before was to avoid that the denominator diverges when the two frequencies are equal. But this is a real number, and those Matsubara frequencies, as you can see, they're never zero. The Matsubara frequencies, they avoid the real axis all the time. So this, in that case, can never be zero. So this I omega n plays itself the role of the regulator. So in that special case, you actually don't need to add this. You can add it if you want, but it's not needed, because this is already providing the regularization in that case. Now, you're right. I mean, if I really wanted to be complete here, I should add it for the special case when z is a real number. So that's correct.
Good, thank you.
Okay. So starting from the spectral function, what we see in the complex plane is that all the functions, the retarded one and the Matsubara one, are actually just sons or special cases of this more general guy here. So if you want if I take that function and I evaluate it along the imaginary axis on those I omega n, this guy becomes the Matsubara G of k I omega n. And if I evaluate it just above the real axis here at omega plus I eta, well, in that case, this is nothing but the G retarded of omega. So that's why those two functions are really the same. They all come from one general function, which is defined everywhere in the complex plane from the spectral function. And according to where you evaluate it, you can either get the retarded function or the Matsubara. And in principle, if you know the Matsubara or if you know the retarded, you can get the other one. And this is a procedure which is called going, if you want, from here back to the real axis. This is called something which is called analytical continuation. And it's mathematically in principle possible, but it's in some cases really very difficult. So it's quite easy to start from the retarded, because when you know the retarded, you know the spectral function, because it's just its imaginary part. And once you know the spectral function, you use that formula here to get the Matsubara-Green function. Going the opposite way, starting from the Matsubara and getting to know the G of R, the retarded, or getting to know the spectral function, is something which is very difficult in practice, because it's a mathematically ill-defined process. And it's a pity, because many algorithms, they give us a Matsubara-Green function, and we would like to have the spectral function to connect to experiments. But that procedure, that analytical continuation, is a very difficult thing to do, unfortunately, even though there are tricks to do it. Great. I think I'll stop with the formalism here. It's 10:15, so I'll start doing a bit of DMFT, and I'll finish tomorrow. But maybe, well, first of all, do you have questions? Okay, if not, I have some for you, so which are all related to this many-body formalism, and so we can give it a try. Oh, there we go. I see some hesitation around question 3. But there's some clear trend with number 2 at least. So definitely, you're right. There's the same information in the spectral function as in the single particle green function. This is a correct statement. Those two guys have the same info. You're also right. The single particle green function, it doesn't contain all the information about the system. It contains information about single particle properties, single particle excitations. If we wanted to have more information, we would need more general green functions, which describe different response functions in the system. So for the last one, the Matsubara time, it's important, even though it's called an imaginary time, it's an imaginary time because we start from the real-time formalism and plug in an imaginary time in there. But after we do that, what we obtain for G of tau, it's important that tau, you have to think of it, this is a real number. It's between 0 and beta, okay? And the spectral function cannot fully be obtained by ARPES. And the reason is that Fermi function that multiplies it's the fact that the ARPES experiment only probes occupied states, so it doesn't provide information about empty states. So you basically only get half, or essentially half of the spectral function here. Great. Well, while you're at it, you can try with those.
A question about nomenclature. Why is it called retarded Green's function? They're advanced Green's function.
Yeah. So like I said, there's actually a full zoo of Green's function, especially when you work in real time and want to know the real-time dynamics of a system. Then you actually need more Green's functions than what I've shown here. Equilibrium simplifies a bit the things. So when you really work with out of equilibrium systems, you'll work with retarded Green's functions, advanced Green's function, Keldysh Green's functions, lesser Green's function, greater Green's. There's a whole zoo of them. They're all very similar in spirit, so they look a bit the same, but they carry slightly different information. So definitely it's called retarded basically because it describes processes that are causal. I mean, there's a theta of t minus t prime in front of it. So it's 0 for when the event happened before you send the particle. So it's retarded in that sense. But there's one which is the opposite, which is the advanced. Yeah, that's why it's called like this. Great. Well, that's great. It's true. Once, if I had the retarded Green's function, I would very easily obtain A by just taking the imaginary part. It's also easy to obtain, well, it's very hard, that's what I said, to obtain A, unfortunately, from the Matsubara Green function. This is the analytical continuation problem. It's a tough challenge, and there's no systematic way to do this precisely on sort of noisy data. If you have an analytical formula, you can always do it, but if you have an analytical formula, you basically already know your spectral function. But if you have G out of a simulation, it's very hard to extract the spectral function. And yes, the self-energy describes all single particle correlation effects. That's encapsulated in the self-energy. And the last one is, actually, I'll finish with this. I don't think it makes a lot of sense for the 10 minutes that are left that I really go into DMFT. I'll actually come back to that last point here about any correlator. Can it be expressed as a determinant? I mean, this I did not discuss, so let me discuss that, and I'll end with this today. Let me go back to my notes. It's actually a theorem. It's a super important one that we will not be using this within the context of dynamic mean field theory, but I'll use it when we talk about algorithms. It's something that is called Wick's theorem, and it's a particularly useful theorem. What it says is, like I said, there are single particle Green's functions, but in many cases, we end up having to compute a higher order or correlators that involve more particles. And so many times we end up having to compute an n particle Green function, which is an object which depends on 2n imaginary times. And which is sort of a generalization of what we do with the Green's function. It's a correlator of, so there's a time product, but this time it involves n destruction operators and n creation operators. I'm running out of space, of course. Like this. So many times we have to compute objects that involve n particles. It creates n particles and destroys n particles. So it's a generalized propagator for n particles. And this is in principle a very tough object to compute in the general case. I mean, that's if we were able to compute these guys easily, then we would be able to have lots of properties of the system. But in general, it's a very difficult thing to compute. There is, however, one special case where this can be done quite easily, and this is for non-interacting systems. So I've put a little 0 here to indicate that I'm now looking at non-interacting Hamiltonian age 0, if you want. So something which is purely quadratic, okay? And that doesn't have correlation effects. In that special case, that correlator that we just wrote can be computed using just products and sums of single particle Green's functions. So this G0 in that case can be written as a determinant of a matrix which only contains single particle propagators like this. It's a matrix whose elements, if you want, are organized like this. So in a given row, you will have the first element always being tau1. This involves those times tau1, tau n. So if you want, you associate the rows to the different values of tau1 to tau n, and the columns to the different values of tau1 prime to n prime. And you fill that matrix like this. So the next element here would be G0 tau2 tau1 prime. It would go all the way to G0 tau n tau1 prime. This last element would be G tau n prime, and so on. I think you suppose you get the point. So you fill the matrix with those single particle Green's function, which is in general something that you know. We've seen the expression for a free fermion. It's very often something that looks simple. You fill a matrix like this, and you compute its determinant, and this is giving you this many-body or many-particle correlator. Again, very important, this formula is only valid for non-interacting systems, right? For an interacting system, this formula, such an expression cannot be obtained. So this is going to be an important result we'll need when we construct the quantum Monte Carlo algorithm. Okay, so let me, well, maybe first ask if there are questions.
So there are a couple of questions in the chat, but I think maybe it could be more lively if people just
speak up.
ask the question. So please, so there is one, okay, by Rakshiv, please.
Yes, can you hear me?
I can.
Yeah.
I just wanted to ask whether it's all on the same site now, so the fermion operators.
Yeah, so it's sorry, I did not. Of course, I could put every time. So you can think of tau1 here being both a time and a position index. So this could be G0 of R1, tau1, and so on and so forth. And then you would have here the propagators corresponding to R1, R1 prime, and so on. So here I just wrote it by just putting the imaginary time tau to make the notation easier. But actually this can be, of course, also can include the position, the site index, or if it's written in a reciprocal space, the K index. Yeah, sorry, I did not mention that, but this is more general indeed. So it's not true just for the local, it's true for the position dependent too.
Thomas Michel has a simple question about Fick's theorem.
Hello, I don't know if you can hear me.
Yeah, I can.
Okay. So I just had a question. Is this Wick's theorem in any way linked to quantum field theory, Wick's theorem, which is used to
Sure.
write like large sum? Okay.
No, it is the same. So this theorem it's the same Fick's theorem as the one that you meet in quantum field theory. It sometimes takes a slightly different expression. So in quantum field theory, you often end up with a path interval, and you have some sort of generator. But basically, what compute is a very similar object as this one. You also compute an object which looks like this. So sometimes it depends a bit on how you formulate it, but you may have some normal order that appears on top of this in the case of quantum field theory. But it's very much the same theorem. Yes.
Okay. Thank you.
So very good. We already had a lot of questions, but yeah, we still have a couple of minutes for some more if you want.
What I can do, maybe I can just flash 2 slides to sort of summarize what we did so far, and if there's still a couple of questions, we can take them before. I just want to go through what we saw and what we will use next time. An important object to sort of probe the properties of the system is this retarded Green function. It doesn't tell you about everything, but it gives you information about single particle properties that are, for example, relevant for ARPES or scanning tunneling spectroscopy. It takes this formulation in real time, but importantly, it's related to an important object, which is this spectral function, which relates to experiments. And you can always bring it down, this G of R, under this spectral representation here. For free electrons, try to remember this one. If I just have one excitation at K, it writes simply as 1 over omega minus epsilon K plus some regularization here. Eta is a small positive infinitesimal. If you have interactions, this will become more complex, and in general can be described by that important object, the self-energy. I forgot the dependence in K here, which encapsulates all the correlation effects. Now, at equilibrium, and mainly because of algorithms, or Monte Carlo algorithms, many of the things we obtain are actually slightly different Green's functions, which are Matsubara Green's functions. They have a definition which is a bit different. It's similar, but it's minus the product of those two operators. They need to be time ordered. So this will put operators with largest tau on the left. And if you have to exchange them, you get a minus sign. You can Fourier transform this also in frequency space, and then you get the information on the Matsubara frequencies, which are defined like this. Tau is a real variable, and it's enough to have the function defined between 0 and beta, because the function is anti-periodic, so you have all the information over this interval. This guy has also a spectral representation, and it involves actually the exact same spectral function as the retarded one, okay? So for the Matsubara frequency one, again, the free electron is just 1 over I omega n minus epsilon K. And in the same way as for the other one, if we have correlation effects, we can describe them like this in a self-energy, which contains all the information about correlations. Very good. Last thing is the Fick's theorem, sorry, but we just had it, so I'll go quickly. If I want to compute a correlator in a non-interacting system, this n-particle correlator can be expressed as a determinant that only involves single particle Green's functions, which is an important result for what we'll do later. Great. And next time, I'll start with DMFT. So do you have any questions?
Well, okay, I see 4 questions in the chat. So let us start with the first. Okay, Sani Ghosh asked a follow-up question about the Fick's theorem. So please, Sani, yeah, take the mic.
Yeah, so I just wanted to ask, if you turn on the interactions in the and you want to consider the Fick's theorems, in like just like the QFT case, isn't there going to be some kind of a diagrammatic expansion you can do, which will kind of give you the similar structure to compute the in particular Green's function in non-interacting case?
Yes, so that will be the what we'll try to do next time. So of course, there's many different quantum Monte Carlo algorithm, but the one I will describe next time is called an interaction expansion continuous time quantum Monte Carlo algorithm. And the spirit of that approach is to construct a perturbation theory in U. And that perturbation theory we'll be constructing is exactly, for those who've done it before, the construction that usually leads to Feynman diagrams. And when you do that, as you construct your perturbation theory, you basically generate terms which are correlators like this that you need to compute. So all of these correlators, if you want, they very much, you can think of them as a bunch of Feynman diagrams that you need to evaluate. We won't actually have to go to diagrams because we'll rather compute those kind of correlators by using determinants. But yes, these are the guys that you meet when you construct a perturbation theory around the non-interacting limit.
Thanks.
Now, Ludwig Rusa has a question.
I was just wondering about the origin, why the Wick's theorem is not valid for the interacting case. And I was thinking that this might be because then the Hamiltonian is no longer quadratic. And
exactly. So yeah, the reason, exactly, there's something special about the Hamiltonian being quadratic. Basically, if you want to think in terms of a field theory or something like that, the fact that the Hamiltonian is quadratic lets you do an integral. It's like a Gaussian integral. So it's something you can carry out explicitly, which actually leads to those determinants. The moment it's no longer quadratic, you can't carry out this integration exactly anymore. And that's the reason.
All right. So now Darwin Vanish has a question. Darwin, please.
Yes, can you hear me?
Yes.
Okay. I was just wondering if, let's say I know the single particle Green's function, so I've computed it. Is there a simple relation between this function and any single particle observable? So any any expectation value of an operator of a single particle?
So
can I...
Okay, you're talking about Matsubara Green's function, I suppose.
Yeah.
Because of course, if you know the retarded one, then you have direct access to the spectral function, and then you can relate to experiments like RFS or scanning tunneling microscopy. If you get the single particle Matsubara Green's function, like I said, it's tough to get the spectral function because it requires analytical continuation, but there are other observables that can be computed from that directly. For example, averages of some correlators like double occupancies. For example, the average of n up and n down being on the same sites. So this is something that you can obtain from, so let me write it, objects like average of n up and down on a given site. So this is something that you can compute directly from the knowledge of G, even in imaginary time. There's also kinetic energy, basically, that you could get. So you can get energies. And yeah, that's the sort of thing you can get directly from G. So it's good at computing static correlators because then it doesn't really involve the imaginary time directly.
Okay, thank you.
All right, so next question by Marc Villain.
Hello, can you hear me?
Yeah.
Yeah. Well, first, thanks for this lecture. It was very nice. It's a very simple question. You said that the retarded Green's function gives the information of the single particle phenomena. Is that right?
I missed the sentence that what uses the single particle information?
You said that the retarded Green's function gives information about single particle properties, but it also allows to include the interactions effect via the self-energy, right?
Yes.
Okay, so
if you want, it describes single. Okay, I understand what you mean. No, when I mean single particle effects, I mean excitation where you excite a single electron, but of course there's many body physics behind it. So this excitation itself generates a lot of other excitations in the system that are many particle excitations. So yeah, don't misunderstand what I'm trying to say. When I say single particle excitations, I think of the fact that the function itself involves just the construction of a single electron. But of course, it does know about the physics of the fact that this excitation will be surrounded by a cloud of other excitations. So it definitely describes many body physics. and many body, I mean, and n-body excitations. But the correlator itself just involves a single particle. That's what I mean. But you're right. It's very important to emphasize this. I'm not doing a band theory. This goes completely beyond band theory, and it fully describes the excitation via all the cloud of interaction that is around the excitation of course. Good point.
Okay, thank you.
Okay, so we have 2 more questions, and then I think after we should make a short break. So Saptarshi Mayunda has a question. Can you?
Yeah, can you hear me?
Yeah.
Okay. Thank you for the lecture. And so I wanted to ask that, so if we apply this Weeks theorem, can we say that the correlator for odd number of fermions is 0?
No. I mean, a determinant of the matrix can have an odd number of rows and columns. It's nevertheless going to be. There's no the G's that enter this matrix don't have anti-commutation properties. They're just numbers, right? So these G's are just numbers. So even if you had an odd number of fermions here, you'd be fine. But there's never an odd number of operators, right? Because they always come in pair. So the 3-body G0 has 6 operators in there. So there's always as many C dagger as C, right? So no, this is also non-zero for odd numbers.
Okay, thank you.
Okay, and our last question by Edith Juko. Please, Edith.
Okay, thank you. I want to know what was the...
We don't hear you very well. Can you, I don't know, either speak louder or closer to the microphone?
Okay. What does the Matsubara green function solve compared to the rotated green function? And in which context can you choose one to the discriminant to other? In which context can choose one to other?
So I hear the music better than the question, but I think maybe I misunderstood the question, but I think you're asking when I should be using Matsubara Green's functions and when I should be using retarded ones. In terms of trying to connect with experiments, if I had the opportunity to work with retarded Green's function in real time, I think they carry more physics, they're more physical, and they will let you an easier access to physical quantities. So if one can use them, you're probably better off working with retarded Green's function. But in practice, algorithms like quantum Monte Carlo algorithms have a much harder time computing this guy rather than computing the Matsubara Green function. So in practice, sometimes we're just forced, if you want to work with Matsubara Green functions, because those are the guys that are most easily computed by numerical algorithms. And then you have to try to work your way to the spectral function using some tools for analytical continuation, which is, I mean, they do exist, but they're tricky.
Okay, so I think now, okay, I can probably read what is written in the chat because it summarizes perfectly the situation. So it's by Martin Gembe. Great first lecture. Thank you, Michel.
Well, thank you, guys. Well,
yeah, that was very, very lively. We had a lot of questions, so I think it's really what we want this school to be. So very nice for this first lecture.